talks by eminent scientists from India and elsewhere. And today he is our speaker for this, ongoing set of talks to celebrate our 60 years. And nobody can be better than Professor Mani to introduce him, because he knew him from very beginning. And I thought, initially I wanted to introduce him, but after seeing him, I realized that he would do a better job of introducing him and also tell about the speaker today. I request Professor Mani to introduce him. Thank you.
Is this on? Is this wrong? Well, this is a pleasant surprise for me. I was not even sure I will be able to come to the talk. For some reason, I have a class today. I had cancelled it because many students were away. They are going to take GRE exams, so they were. Anyway, it's a real pleasure for me to introduce Jayanta. I know him from 1980s onwards, and various things which come to my mind, and let me just briefly tell you that. I was already in IIT Kanpur, and that time I was visiting University of Virginia when I came to know about Jayanta, and Jayanta called me saying he is going there. I said, sure, you should write, and we will see that it happens. Actually, what had really happened was something earlier, which in some ways was a strange thing. I had heard from others that he had given a lecture in Washington about his thesis. Please correct me, Jayanta. Kamalesh Kar is the person who told me this. And the lecture essentially started saying that there are 2 or 3 important problems in solid-state physics at that time. And I have just solved one of them. And then he went on showing that in great detail. And Kamalesh Kar was there in the audience, and he mentioned that to me. So it struck me. So when I went to Kanpur at that time and dug out his papers, and of course, they were fantastic. And we got it moving. Fortunately, Kanpur, things moved very fast at that time. Ramachandran was the head, and then at that time we went to the dean. Everything worked out very well. Fortunately, he came, and he started courses. There, I'm sorry I'm taking a little longer, please excuse me. There, normally, we people teach 1 course a semester and 1 tutorial. Here he comes, he takes 2 courses a semester, and 1 Physics 101, which has 400 students, which is the most difficult course to teach. So he absolutely set an example of what we were all sort of felt this is very inspiring, he should be doing this. And of course, he came out to be a fantastic teacher there, continued his research in many ways. I learned a few things from him. He gave a set of lectures in Turbulence at 2 or 3 places which I have attended. They are absolutely top class, as you will see now. And then from there, I moved to Allahabad. Then he moved to Kolkata at that time. And later on, also he moved to Allahabad, and we interacted for quite some time. Then again, he has gone back to Kolkata. I have not met him in Kolkata, but I have not been there either for some reason or the other. So it's really a remarkable travel that he has done. He has helped many, many students, and many students have finished their PhD with him. And those who worked him were really inspired. I've had a chance to meet many of them. They swear by the quality of work that he does and the speed with which he can finish calculations. So it's a pleasure to invite Jayanta, my friend. Please start.
So what we are going to do is talk about turbulence. And the thing which we need to know is what exactly are we talking about. And it's going to be about dynamics. And that dynamics is, the characteristic of that dynamics is that dynamics is very difficult to predict. So this is what one means by the dynamics being chaotic. It's unpredictable, and I had a proof of it very nicely last evening, because for the last 3 or 4 days, there was a cyclone originating in the Bay of Bengal, fairly south, and there were predictions about its path, and it seemed that 25th would be a bad day to travel, and then it turned out 26th is a bad day to travel, and so on and so forth, and it seemed that it would be wiser to travel on the 24th than 25th, and so on and so forth, until actually when it happened, it turned out that 24th was much safer to travel, and actually Calcutta was not affected almost at all. I mean, maybe a little wind and so on. So that unpredictability, that's there. I mean, you see it so often when, I mean, when we were young, we made fun of weather forecasters, and then gradually, I mean, it was a revelation when one learned about it, that the weather forecasting is not exactly a very easy thing to do. And you do see things go wrong, but you can't complain. And so that is what we are going to be talking about. But in a slightly different, you won't see the time part over here, because that is more let's say, calculational and technical. What you will be seeing is what is turbulence, which is essentially the same thing but in spatial patterns, and therefore it is, while more difficult in one, because to get the spatial pattern is no easy job, but at least it is more, it's easier to talk about. So that's what we are going to do, talk about turbulence, and so we get started. It is, to make life simple, it's going to be homogeneous, isotropic turbulence, so all directions are the same. There is no particular bias in the pattern in in the fluid flow. The simplest example which one takes is the stirring of your coffee in the cup. You stir it not too slowly, and the pattern that you see would be rather complicated if you look at it well, carefully. And the striking feature essentially being that the velocity which you see of this swirling fluid is a random function of space and time. And the goal then would be that if I say it's a random function of space and time, then I have to tell you what the probability distribution is of that, what is the underlying distribution function which is making the velocity field look random. But that again is rather too difficult a problem. So you scale it down and say, I'll be satisfied if I know the moments. And among the moments, you start with average of v is obviously 0. So you want to go for the second moment, which is, as written over here, the difference in velocity between two neighboring points, and ask for the square of that averaged over all space. This is the typical thing which everybody shows, and so it's worth pointing out that here is a drawing of Leonardo da Vinci, which I mean you must have seen 100 times, but still let me point out that what is after is this whole mess of fluid over here, and then he had the vision to understand that this whole mess is repeated on a smaller scale over here and on a still smaller scale over here, and so on. So this pattern repeats itself from scale to scale, and therefore there must be some kind of scaling law in this pattern over here. You can take one small vortex, magnify it, and you could get the larger one. So it's a question of getting the scaling right, and that's where in 1941 Kolmogorov entered the picture, that what would be the simplest way of getting a handle on this scaling law. So he looked at as the simplest thing, as always it's good to look at the simplest, and the simplest is what we had written down, the V times V. So this is written in momentum space, and this has a physical meaning. Integrated, this correlator, integrated over all momenta, wave vectors, gives you the energy of the system, total energy of the system. What Kolmogorov did was defined an energy spectrum, that how much energy is contained between the wave numbers k and k plus dk. So that's E of k, and that is the energy spectrum. So question is, what can I say about E of k? Who determines it? Obviously the dynamics does. So the dynamics has to determine the E of k. Now what is the dynamics? The dynamics is the usual hydrodynamic equation, which is the acceleration of the fluid. This is the partial with respect to, this is the total time derivative. This part is the standard time derivative. This is the convective part of the derivative. That, I mean, there is a gradient in the velocity, and therefore as you move along, there is going to be change with respect to time. So the local v will change with respect to time by this factor over here, and the repeated indices are summed over. So this whole thing is the total time derivative. On the right hand side, Newton's forces. Here is the pressure gradient, which is always there. This is the viscous dissipation, which is there in hydrodynamics, and this is some random external force, which maybe you imagine that if there is a maintained pattern, then you must be doing something, and otherwise it would not be maintained. Without this f of alpha over here, things would have to decay, the pattern would have to decay to 0. So whatever the pattern is, this distribution function, if it is a maintained situation, there has to be an external, what is called a stirring force, keeping your coffee stirred if you want to keep that pattern there. So that is what this f of alpha is. You assume the simplest situation, incompressible flow, and that means the divergence of V is 0. So that's what you need to do your maths on. It is, the problem is that, all right, before the problem, having this constraint over here removes the pressure in terms of the velocity, because you take a divergence, assume this force to be divergence free, and immediately the velocity is expressible, the pressure is expressible in terms of the velocity, so the pressure is eliminated by this condition over here. So that makes life simple, and so now the point is, the thing which one wants to look at, if I want to go back to this, then you want to look at the energy budget. So you want to look at the energy budget So if I multiply by V alpha over here and integrate over all space, then I would be finding that this part becomes the change of energy. Then there is this part over here, which if you integrate, we can take my word for it that it will get 0. V alpha integrated, d alpha p integrated over all space, again 0, assuming that velocity falls off at large distances. This one is non-zero, neither is this 0. So this is the rate of change of energy, and that is what you see written out over here. The rate of change of energy is the dissipation, and there is this, which is the force which you are applying, which is stirring energy, which is sending energy into the system, and the system dissipates it by this viscous action. So here is the energy balance. And so now you look at this energy balance and you see that this part has no derivative, and all spatial scales are good enough for it. So it will be operative at large lengths, large spatial scales. This one over here, however, has a preference. So preference is that there is a derivative over here, so small scales are the preference for this term over here. This dissipation acts at small scales. Your stirring is at the edge of the cup, and therefore it is at the large scales. So this is a small scale effect, length scale effect. This is a large. So input at large scales, dissipation at small scales. So the steady state. So now you have a non-equilibrium. Things are not in equilibrium because there is this external force being supplying energy over there. But there is a non-equilibrium steady state where this is equal to 0 and this part is going to be equal to this part. So this is the kind of state we will be talking about. It is not an equilibrium state, but neither is this steady, neither is this unsteady evolving stage. It is a steady state where the rate of input of energy is equal to the dissipation rate. Now the question of scales at which they operate. Well, the scales are to be determined, as I said, it's always the epsilon, the rate at which you are supplying energy, that will be determining whether you are supplying it or dissipating it, because the total energy has a dynamic balance, and the viscosity. If you work things out, this V bar is the average velocity. The length scale that you get, I have removed the viscosity coefficient by some standard manipulation in terms of to write things in terms of epsilon, and you get this scale over here. The other scale is very clear, much easier to see, that it is where you are putting in the energy. So the energy input rate, which is V average squared by T, and T replaced by L over V, and so the energy input rate is V cubed over L, and that is what this is. So this is the large scale, this is the small scale. The ratio is the ratio of the Reynolds number, which is something which is defined as velocity times L by length by viscosity. So if you work things out, this ratio, which is 3/4, what I'm saying is that this will work out to be the Reynolds number, V times. So Reynolds number, a buzzword in everything. Large Reynolds number, that's where you see the nonlinear terms dominate. Small Reynolds number is linearized hydrodynamics. And the length scale difference, where you are putting in the energy and where you are dissipating the energy, is Reynolds number to the power 3/4. So if Reynolds number is very high, you have a large separation, a widely separated scales, and that range of, so this is the 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 range of, so this Our concern will be with the scale which is far away from both capital L and small l, and that is what is called the inertial range. So this is all Kolmogorov. That is what Kolmogorov defined for us, that there is this inertial range where his claim would be that life is certainly much simpler than what it would be at large scales where there is stirring going on, or at small scales where there is dissipation going on. So Kolmogorov separates the scale to begin with, and you see what happens is that if you look at the energy spectrum that I had talked about before, if you now look at what the energy spectrum E of k, that is what the y-axis is, the log of, there is a log-log plot, and this is k over here, sorry, off goes it. There's a k over here, and you see that there is a linear region over here where the ek scales with k. So this is a few years old. The power law, the exponent ek proportional to is k to the power minus 5 by 3. That's this line over here. This is 1024 cubed in which the computation was done. Today that number is up to certainly the 4096 is common, even bigger are there, and the thing is that the answer still remains very, very close to 5/3 all the way down. Over here you are seeing the dissipation range split off. So 5 by dissipation takes up over here, but if you push this back another 2 or 3 decades, you still see, before the stirring takes over, you see the Kolmogorov thing being quite valid. So it is real. I mean, at least it's real numerically, and it is real in the lab. In the lab, there are hundreds of other things which the experimentalists have, but 2 to 3 decades, no doubt about that. All right, so what did Kolmogorov do? Kolmogorov said something almost trivial, that if you look at this range over here, in wave number space, it is small k0, that's k0 is 1 over L, and this is kd. You look at the energy spectrum, what could determine the energy spectrum? The energy, so what's happening? We are putting in some energy at large scales. It is filtering down to small scales. So, because there is a steady state, it is the same amount which has to filter through every stage, and therefore this rate is the rate at which the energy is flowing through the system. That is a parameter, and so is the wave number k. So E of k is going to be determined by these two chaps alone. Do a dimensional analysis, and Ek is proportional to k to the power minus 5 by 3. This was Kolmogorov 1941, and that essentially started out this whole game of trying to understand what's going on. Well, if you look at it in R space, you look at the velocity difference between two neighboring points and dot it with R to make it a scalar, raise it to the power n. The Kolmogorov argument would give you this. So if n is equal to 3, you should get epsilon times R. Kolmogorov actually started from Navier-Stokes equation and proved that that is correct, and that's the only exact answer in all of three-dimensional turbulence, that this 3 power v delta v to the power 3 average is minus 4.5 epsilon r. So that is beyond any doubt. So this is extremely important thing to have, because you will sort of if you do anything, and if you try to extend it a bit and this law fails, then you are gone. So it's a tremendous check on. So all right, what about n equal to 2 in a space k to the power minus 5 by 3 there? In the coordinate space, it corresponds to r to the power 2 by 3. This constant c over here, large number of numerical work and experimental work seem to suggest a number close to about 1.8. All right, so now we are very good, but let's try and talk about n equal to 6. So this is v cubed. So we are talking about the question of v cubed. So this is delta v to the power n, where n is 6. So now what is the significance of this v cubed? You look at the local energy transfer rate, it has to be v square over t. It's dimensional, this talk is going to be dimensional analysis all the way. So it is v square over t, and t is r over v. So the local energy transfer rate is the local velocity cube divided by the local length scale. So Kolmogorov says that the local energy transfer rate is constant. So energy, because the picture on which Kolmogorov built his theory was that the energy gets input at this large scales and continuously transfers down to the lowest scales where it is dissipated, and there is a non-equilibrium steady state where this continuous no loss flow of energy. If that is so, this epsilon r is scale independent, and therefore v cubed has to scale as r square, which is what the previous formula would give you. The one over here, you put n equal to 6, you get r square. So that's just getting, but now you see the experiments and the numerics, it gives you not r to the power 2, but r to the power 1.8. And here comes the first conflict. So you have to you bring in what in critical phenomena used to be called anomalous dimension, and therefore E at local E at x and local E at x plus r scales as r to the power minus mu, and is not a constant epsilon square. So this is what is called intermittency. Intermittency, for you'll see why in a minute, it is because this the state which Kolmogorov pictured is this whole energy cascading down without any problem. This over here is implying that there are blobs where it is not doing so, and therefore it is called intermittency, and the deviation from Kolmogorov in general that gets clubbed as intermittency. All right, so Kolmogorov himself was sort of had to try and fix it, and what he did was essentially what we today would say is that he looked at his way of doing it in 41, where the epsilon was considered a constant as a mean field theory. So you picture this, what I have been saying so far, as a mean field theory where the mean field is in the energy which is flowing down the scales. And Kolmogorov and Obukov took the stance in 1962 that instead of saying that this is a constant, use a distribution, a mild distribution for this energy epsilon, a distribution which would, epsilon is positive, so but you want the distribution to be from minus infinity to plus infinity, so change to log r and log epsilon, and therefore it's a log normal distribution that the log of epsilon has a normal distribution. If you do that, you calculate the local epsilon to the power p by 3, you get an answer which is like exponential this pm by 3 p squared. So that's all. So, but now what you can do is you look for, you get the velocity raised to the power p because of this, epsilon r is v cubed, and you can compare with the exact result of p by 3 and establish this m and sigma is related by this. And now you have all the moments in terms of epsilon bar and r no longer following the old Kolmogorov wisdom, but nailing it to the fact that there is this intermittency using a distribution and nailing the distribution parameter at the only exact result known. Well, this does things somewhat better, but still not the final answer. So, so things are a little more complicated, and so all of 80s and the couple of decades through the 80s and 90s, people looked at what is Spotiness of the turbulence process, that the dissipation takes place at all scales. So every scale that you look at, there is a certain amount of dissipation, and the invariance under this scale transformation, Navier-Stokes equation would have is invariant, and the local dissipation rate scales as alpha minus 1, and so alpha, if you recall this dimensionless, that would fix a value of alpha, but you can't do that. That is what went wrong. So you play games with it, which uses a lot of fractal picture and so on. I won't go into that, but the best picture of that was actually a very nice way of thinking by Srinivasan and Menevo, which is very, very nice, and therefore I'll spend a minute or so on it. That you imagine that there is this energy at a large scale, and then it breaks up into 2 bits with probability p and q. So p goes left, q goes right, and then again the same thing happens. P goes left, Q goes right, same over here. And what you do, you want to continue this cascade all over. So you are picturing this. This is essentially that you are in a one-dimensional line. This dissipation process is taking place. You get an effective dimension of this set over here and add 2 to it in a 3-dimensional space. So this would be like a Cantor set, and you get a Cantor-like set, you get the fractal dimension for it, add the 2, and you can get a picture of the e to the power, the delta v to the power n, and so on. So that was this very nice way of picturing it. It is not it gets you the fractal dimension as what I show over here, and works very well, but not well enough to be the final answer, not supposed to be either, but then it certainly led to further works, more complicated, but at the end of the day, very good fit, but to many low, but you can always go to a higher moment where it doesn't work so well. And so things remain sort of a bit, you don't know what the final answer is, let's put it this way, but you have a fair idea that what you know for certain, that the Kolmogorov picture is good, but it has a fault which is at the 10% level, that for the picture being that it is continuously cascading down, that is not true. So you want to correct for that. You get various ways. I mean, first you do the simple-minded thing which Kolmogorov and Obukov did, and you get a distribution of the postulate a distribution of the energy clumping and get an answer which takes the 10% to maybe of the order of 1 to 5%. And even that is not enough. Then there is this Srinivasan-Menevo result where you think of it as a fractal set, try to get the fractal dimension by some clever trick or other. This is the simplest to talk about, does very well. I mean, it's better than 1%, but no, so anyway, the others which are there are also of that order, maybe slightly better. But at the end of it, there is, I mean, quantitatively, you don't have an answer which starts from Navier-Stokes equation and tells you that, look, do this, 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 and this, and here is the answer. That is not being done or not even attempted. So that was the energy cascade and so on. Energy was a conserved quantity, and so there were. Now, before I leave this, see, why don't, there are other branches of physics which were very difficult, like critical phenomena, for one, various aspects of high energy physics in another, and they got out of the mess in some ways or other. And why didn't turbulence get out of that mess? The problem lies in this inertial, everything you want is in this no man's land called inertial range. Critical phenomena wanted it asymptotically at the large length scale. The correlation function becomes infinitely big, and you want to look at that. So there was the renormalization group fixed point, which corresponded to the infinite correlation length, and you had a starting point. High energy physics went the other way, and there was this question of asymptotic freedom, which helped the things get moving. Over here, you can neither go very far there, nor can you go, it is all, you are supposed to do it in the middle, and this inertial range, and get it out. And that is where all hell breaks loose. So if there were a clever way of going whether to that limit and coming back, or to the high, the low R limit and coming back here to the intermediate R, that would be, but the point is that neither of the two limits are, because each are sort of important, and therefore the way of handling one without the other seems to be a mess. But that's what it is. So that's d equal to 3. We come to a different complication in d equal to 2. D equal to, over here it was just the energy flowing. Energy was the only conserved quantity. That was the only chap who had the right to flow. D equal to 2, there is another conserved quantity. So here is what we define a new quantity we can call a vorticity, which is this curl of V, and curl of V has only one component in d equal to 2. And if you look at this S, which is omega square integral, it's called the entropy, and that's also a conserved quantity. So you have two conserved quantities. You have energy, you have entropy. Which way do they flow? So that's the, now that you have two of them, you have to worry about whether both of them flow from high k to large length scales to short length scales, or one of them goes one way, the other goes. So there has to be, so you have to decide. Now how do you do that? So that's the, this is the new twist when you have more than one conserved quantity in your system. So so I want to focus on something where this is quite trivial but very interesting. And this wasn't, I mean, to get this far in the argument was actually not very long ago. I mean, a couple of decades maybe, but no more than that. So what you do is focus on the nonlinear term and look at the rate of change of energy. So V alpha minus k, V alpha dot k. And that's the nonlinear term here. It is V with at momentum p, this at momentum k minus p, and this at minus k. So there is this, what is acting, what is at the base of the change in energy at scale k is this triad over here. And so the process, this triad has, if I think of it as p, q, and k, this is a triad with p plus q plus k equal to 0. And you need to consider all such triads and come to the pure picture of which way is a conserved quantity flowing. All right, let's just instead do a one triad thing. It is k, 2k, and minus 3k. So that satisfies this p plus q plus 2k, and with the energies E1, E2, and E3. And impose the conservation laws on this triad. So I'm going to have, so E1 plus E2 plus, so that's conserved. So it is delta E1 plus delta E2. If I have a variation, then delta E1 plus delta E2 plus delta E3 equal to 0. The entropy is k squared times the energy dimensionally. So the corresponding entropy conservation tells you that it is delta E1 plus 4 delta E2 plus 9, it is the 2 square and the 3 square over here, that's equal to 0. You solve for it and you get delta E1 in terms of delta E2, which is the middle chap over here. So delta E1 is minus 5 by 8 E2 and delta E3 is minus 3 by 8 delta 2. So delta E1 is greater. So delta E1 is greater than delta E3, so energy flows in the backward direction. So with this previous thing, there was this very clear-cut picture where we had the energy flowing from the large length scale to the short length scales. Now you have this two-dimensional system with another conservation law, and you now have to fiddle with both of them at the same time, do this sort of back of the envelope calculation, and you say that, look, energy flows backward and entropy forward. it works. So you do the numerics and you find that that's indeed true. The forward energy entropy cascade, which is in the forward, corresponds to a spectrum of k to the power minus 3. K to the power minus 5 by 3 shows up in the small k region. The entropy shows up in the large k region. All right, so that's as I said, this is just what I said, that the backward cascade, and that's energy, which is k to the power minus 5 by 3. You work it out for the it's in terms of entropy flux, the dimension is this. You do a dimensional analysis once again, and it's k to the power minus 3. Works. But there are lots of problems over here. Number one, is there a log? Is there a log over here? That's a big question, and some other small issues. But at least, I mean, the basic picture is what you see over here. Now you go to another system, which, I mean, the kind of fluid that we are very familiar with, the air in the Earth's atmosphere, but it is a rotating system. So there is the rotation of the Earth, which causes the layers adjoining to it would have some rotation. So then first, next thing what we want to do is talk about rotating fluid, and what do I expect over here? Well, here you expect something problematic because this is the dynamics. That here is the nonlinear term, here is our pressure, which I could remove into favor of the, so I mean effectively a part of the nonlinear term. But here is the Coriolis force, V times omega, and that has to be included. And now if I increase this omega over here, then there may come a time when this eclipses this over here. And then it's no longer a Kolmogorov situation. So when does that happen? So that would require, again, comparing the scale of this, which is V square over L, with the scale of this, which is V times omega. So you compare that and you find out that this is weak if L is big and L's bigger than V over omega, and what that works out to in terms of K is wave number smaller than this omega and this energy transfer rate over here. It is going to be Coriolis force dominated. So you're going to see a crossover. If K is smaller than this, then there is going to be rotation playing an important role, and the energy transfer rate is going to be determined by the angular velocity and the wave number. So it is the angular velocity which is the important chap, and not this energy transfer chap anymore. So it is going to be determined by these small wave numbers by the angular velocity and the wave number. The corresponding answer is you do a dimensional analysis. As I said, everything is dimensional analysis, and this gives you k to the power minus 3. But there is the other fact of this high speed. It's going to confine you to the xy plane. So it is, if omega is in the z direction and omega is very high, then the forces would be larger. You would be confined to the plane over here. So this minus 3, there is going to be a dimensional reduction, and is k to the power minus 2, which you have to compare with the k to the power minus 5 by 3, and over the last 5 or 6 years, it is pretty clear that there is this crossover from k to the power minus 2 to. There is a finer point over here, that there is anisotropy, and so I need to differentiate between k perpendicular and k parallel. So k parallel to omega, k perpendicular in the plane, and so this, what you see as this minus 3 over here is actually, it is k perpendicular to something, k parallel to something, and the addition is the 3, and that I have, that's not, that complication is not worth talking about really, but I mean, for talk of the, but the point is that because of that, that is essentially telling you that at high omega, it is the two-dimensionalization, and the k perpendicular and the k parallel, it is only the k perpendicular which really remains, and that gives you the k to the power minus 2. All right, so finally, the last bit that I want to talk about is that another complication, that I have now a different kind. This was a crossover which we saw, that you went from the spectrum changed from this to this as k changed. We'll talk about crossover once again in the next problem, but it is going to be a crossover of a slightly different variety. So the next one is convective turbulence. That is, I have a fluid between two parallel plates, let's say, and I maintain a temperature difference, and I'll take the path initially, the one which is sort of more colorful, in the sense that if I take the bottom top plate to be hot, and the bottom plate, rather the bottom plate to be hot and the top plate is cold, you have a top heavy situation, and so the movement begins with the top layers coming down, and so that's convection, and convection happens as in the form of rolls, and as Rayleigh calculated, happens at a Rayleigh number of 1708. So 1708, you have convection starting. Below that, it is going to be a static fluid, then the convection taking place, and then as you increase the Rayleigh number still further, the rolls change to wiggling rolls, and then from the wiggling rolls to more complicated wiggling patterns, and then to chaos, and finally to turbulence. So so that's why it's a more colorful thing. After a few minutes, I will have to resort to the reverse situation where it is a stable, this is the unstable stratification. I'll switch to stable stratification after a few minutes to remove a particular complication. But this is actually, I mean, nice physical setting. So anyway, I mean, we start with this. And now the kinetic, so whose spectrum am I looking at? Always kinetic energy. I mean, whether that is right or wrong, I wouldn't be able to tell you, but the point is that Kolmogorov started with kinetic energy. Everybody talks about kinetic. So whenever you see the word energy spectrum of turbulence, even if there are hundreds of kinds of other factors involved. For example, the entropy as entering in through the rotation, magnetic fields entering in magnetohydrodynamics, and the potential energy due to the stratification over here. The spectrum belongs to kinetic energy. So that is something which you need. Otherwise, I mean, things, nothing would make sense as we go along. So all right. So now I need the dynamics is this. Here is the additional force, which is gravity, and here is the temperature is a variable, and temperature diffuses according to, here is the time derivative, and that is the diffusion part. So now the first thing that has to be done is that this one has an equilibrium state which corresponds to constant gradient of temperature. So that I don't want. I want the equilibrium state, only equilibrium state that I want is the zeros. Everything is zero, so which is what it was till now. So I want to make a transformation so that this part is transformed, and we do that little thing, and you do it by using delta T, which is, this is the conduction state profile. You want to remove that from the problem, so you define delta T, which is T minus that, and what you get is velocity. This is your dVdt. Here is the pressure force, here is the buoyancy force, and that is the dissipation, and here is the change in the but it is also driven by the velocity in the. So now there are two fluxes over here. There is the velocity flux, which you get out of this quantity over here, which is the kinetic energy. There is the kinetic energy flux, and there is the other flux which has to do with this nonlinearity over here. So delta T times delta T dot. So this is the delta T square, which is a flux corresponding to the dynamics of the thermal variable, and so we have to deal with now suppose which is the so it's a question of which is the dominant flux. Suppose that it is the Kolmogorov which is the dominant flux, then the spectrum is, as we have seen, that this. But suppose it is not the dominant flux, suppose that it is the temperature flux which is dominant, then you redo the Kolmogorov argument as was done by Bolzano and Obukov in 1959 and 60, and you get, instead of k to the power minus 5 by 3, and you find that it is minus 11 by 5. So minus 5 by 3 and minus 11 by 5. And the urge for most people over the last century was that what you want to do is essentially add what is the total spectrum? You just add this, and the total energy spectrum is a sum over here. And therefore, if you add at low k, this will dominate, at high k, this will dominate. So that is that would happen, and that is what people kept looking for years, and actually never saw it. So if you are in instead of the coordinate space, if you are in if instead of wave number space, if you are in coordinate space, then it is r to the power 2 by 3, and this is r to the power Bolzano is r to the power 6 by 5. So at large r you expect Bolzano, at small r you expect. And what do you see? Well, what you see is something, it's all very difficult numerics, very difficult experiment, but here is one. And what I want you to see, the art, this is S2, and what these are the two, this lower figure is the important one, where you are looking at essentially the this is the lower, the second order quantity. So you are looking at the second order quantities over here, and here you see this is 6 by 5. This part of it is 6 by 5. And that is what you expected at large wave numbers. So this, you see it over here. And then if you see, if you did this experiment or did this numerics, it's breaking off from the 6 by 5 to obviously what is a lower slope. So that is not very good. I mean, this is not what you expected. It told you that it is r to the power 2 by 3 and r to the ux go by, they add, and if they add, then it is 6 by 5 at large r and 2 by 3 at small r. And on the other hand, if you look at this, is not, you can say that this is not the greatest advertisement for saying that 6 by 5 is at lower and 2 by 3, but certainly, I mean, this is bending off. There is absolutely no, and r is increasing in this direction. So there seems to be a problem. So there seems to be a problem, and this is more of the same, and it is the same kind of issue that you look at the, and you don't see where the 6 by 5 where you should see it, and you can use all sorts of words and pictures, it does not help. So, well, maybe we should, what does one need to do? One needs to go back, what we have been saying, who flows. What flows is a conserved quantity. What is a conserved quantity in this problem? The kinetic energy dynamics is given by this. That is what one gets from the velocity equation. It is not conserved in the eta equal to z limit, eta equal to 0 limit. The so-called potential energy, that is the chi square which we had, goes like this, and that's not conserved, that is not equal to 0 when the dissipation is gone. So these are by themselves not conserved quantities. So what do I need to argue? Well, you look at the total, over here, and on the other side now, I only have lambda and eta. So if you ignore the dissipation, what is conserved? You have a conservation law, and conservation is this. So Kolmogorov arguments, which we have been using so far, can only hold for this conserved quantity which is flowing. So that is the only conserved quantity, and if I want to make any Kolmogorov type argument, I have to consider this flux. And if it is pure Kolmogorov, then I would say that K dominates, and if it is pure Bolzano, then it is G dominates. And therefore, the dominance is going to be determined not by whether it was 11 by 5 and 5 by 3 in powers of K, but the calculation has to be based on the fact that here is my conserved quantity, and I have to let the hydrodynamics do the rest. So, well, I mean, that's that, and now it's all right. One small thing over here. This is when I change the signs. you see there is a negative sign over here. This negative sign over here for the conserved quantity comes from the fact that I am heating, I have an unstable situation because I am heating from below. If, on the other hand, if I took a stable situation, if I heated from above, all those fancy things which we talked about, stability, the Rayleigh instability and the oscillatory the waves and so on, and eventually chaos and chaos to turbulence, all that goes away. All that goes away, but what gets you, if I am interested only in the end point of turbulence, then I have a plus sign over here and life is much simpler. So you focus on the fact that if you want to get at that, you look at only the part where it is a plus sign, so it is a stable stratification, and if it's a stable stratification, you get a plus sign, and now you are in a position to, you are in a, you have the potential for getting the Kolmogorov picture, but you know whose flux I have to consider, but there is the problem that how do I set it up? So you to set it up, you look at, I mean, there is a number which is you have to compare the two quantities. You compare the two K and the so-called the potential, the kinetic energy, and this sort of the potential energy, and you ask which is bigger and which is smaller, and if you do that, then you do some rescaling and you find that there is this Richardson number which is determined by the temperature difference delta T, which determines if that is big, then it is potential energy. If it is 0, then it is kinetic energy. So that's how the dominance goes, and so on. And therefore, at the end of the day, so once I have figured out how that this is the conserved quantity, that calculation has to tailor to what keeping that a conserved quantity and doing the hydrodynamics as has to be done with it. If you go ahead and do that, what you get is the strange answer somewhat, that it is Bolzhiano-Obukhov at the higher wave number and Kolmogorov at the lower wave. The crossover happens with the Kolmogorov falling at the large K, the small K level, and the Bolzhiano falling at the high. Then that's what you get if you have the starting point as the conserved quantity is what is the really conserved quantity, and assume nothing else. So that's the way it stands, and that's with the last thing over here. Here is the numerics carried out some almost 7 or 8 years ago on this problem with a stable temperature that is heated from above. And here you see the energy, kinetic energy spectrum, and this is normalized by 11 by 5. And here you will find that 11 by 5 is reasonable, and k to the power 5 by 3 is not reasonable at all. And well, if you look at it, so if the k, so 11.5 is reasonable there, and not so reasonable when you were, I mean, the 11 by 5 is reasonable, but 5 by 3 is not. If you want to be very sort of trying to look at things very closely, you would find that the 5 by 3 does fit this region over here. So if the 11 by 5 is going to go somewhat over, and then if you were to have a 5/3 line, it would probably do somewhat better over here. This is low k, and this is high k. So you can try to sort of push your luck and say that, look, I mean, this is really showing you that it is 11/5 at lower k, but it's not the greatest data with which one can play around. That is there are a couple of others in literature which are of a similar kind. So the thing would be that if people were to do this thing seriously and carefully, numerically or experimentally, and as you can see, it's the reverse in the case of the coordinates. You should be seeing this picture over here. This is actually somewhat clearer. As I said, that over here you see the 6/5 translating, going over to 6/5, going over to certainly a number smaller than 6/5 as you go to larger r. So that is that is in keeping with the statement that in the momentum space it is 11/5 at large momentum and 5/3 at lower. And once again, I mean, the point is that would one be doing, these are pretty difficult and sort of time-taking simulations and so on. But anyway, here is that is the problem. This crossover is a bit which is not really clear at the moment, so there are still many other things to be done. This is one that I know of that is, at least from my point of view, good to look at. So thank you very much.
Questions? Okay, so maybe I will start. So basically, if I understand correctly, right? So if you take different type of turbulence system, so I think one thing, the first thing which basically we look for is the conserved quantity and the flow of it, right? And a priori, it is not clear what is going to play the crucial role, right? In the sense like because you showed in the previous examples, it was just the kinetic energy all the way, right? And only when the, like in the last examples, the potential energy also got added up, and then that became the new conserved quantity, a combination of it with the kinetic energy.
Yeah.
So if you just, if we just look at also a different type of turbulence system, right? So is it like the first thing which we should look after is the conserved quantity, and what is it?
Yeah, so the message is that first look for the conserved quantity. See, when I had an example where there were two.
Right.
It's and the two would drive their own fluxes.
Correct.
And you have the entropy flux going to higher wave numbers, and so if you have two conserved quantities, you are certainly going to see two fluxes and two kinds of scaling from that. With one conserved quantity, you can have two different scalings, but I mean, you can't sort of from two different scalings, you cannot say that I have from two different scalings, I cannot say that there are two conserved quantities. That has to come from the science. That's my point. That I have to, when I'm doing a problem in this area, I have to look for if there is a question, if the Kolmogorov picture, that there is something cascading down, and whatever is a conserved quantity, then that what I have to look at is what is the, if there are two conserved quantities, then the problem arises that if one is the other, is it also cascading down or is it cascading up? So the d equal to 2 example tells you that, look, I mean, yeah, but the energy cascades goes up and this goes down. And when it comes to this one, well, it is just one conserved quantity. And if there are two different scalings, it is not, where you will see that scaling is not going to be determined by which power of k works in which region, but you better do the calculation. I mean, no longer is dimensional argument the answer, because the conserved quantity is linked. The crossover is in the conserved quantity and not, therefore, I mean, what the spectrum, mind you, is kinetic energy. It does not add. Right? It is just, it is no longer, before this we were talking about the spectrum is kinetic energy and whatever, I mean, all right, it is either determined by the conserved quantity and all right, one conserved quantity, and you have, here also it is one conserved quantity. So the kinetic energy has to be, but these two conserved quantities scale in different ways. They have their own scaling, and you better keep that in mind before, I mean, you do anything. So that is the, I mean, power counting is not the way to go about it. That's the point. I mean, that there is, in fact, there is dynamics over here, and you have to look at the dynamics and how it unfolds.
And people, just one more question. So people do tabletop experiments, is it? Like with turbulence, I don't know.
Tabletop experiments don't give you any spectra.
I see.
See, I mean, those would, those were actually good for giving you some idea that a spectrum exists and so on and so forth. So it is entirely numerics. So actual experiments are, I mean, experiments which can accurately probe these. See, you are talking about these length scale dependencies, which are something like 10 orders of, 5 or 6 orders of magnitude. That is experimentally very difficult. So it is almost all numerical experiments.
I see.
So you mentioned that these scalings can be connected to some renormalization group equations and things like that. Are there any studies to find out what are the corrections coming from underlying dynamics through anomalous dimensions?
Yes, right.
Violation of scaling, you know.
Yes, right. The problem is over there that one would like to, does the renormalization group fixed point exist? For that, I actually need to do a calculation. All right, now actually doing a calculation is, I have to do, I mean, so I want to get into that. I would have to actually write integral it would be a loopwise expansion. So it's a loopwise expansion, and I would have to, for example, if I were to do a dimensional regularization, I would pick out the poles from so this is where the difficulty comes in, that if you are, I mean, if you have to implement it, you would have to give the random force a form through which, I mean, because that in the perturbation theory calculation, it would come up as the correlator. So I need to give a correlator form. So there was in the late 70s a model where the correlator was specially chosen so that you could use the exponent of the noise to, I mean, the spectrum of the correlator to set up a perturbation theory. The problem was that in extracting the pole, for example, I mean, if it's a critical, you look at d equal to 4 and there are no other singularity. Problem is, over here, there is an extraneous singularity which has nothing to do with the, and that is why those, they were sort of a question mark about the whole business and but yeah, I mean, there was a sizable amount of literature who tried to use the RG, saying that we will use it as a long distance, we will like to get it in the k tending to 0, so use that fixed point, but that never became, I mean, never was totally accepted, because, I mean, there were these somewhat artificial nature of the forcing that you were putting in.
Okay, are there any further questions?
Hi. I just have a naive question that just like first time I am hearing about turbulence. What is the, like in one sentence, what would be the difference between a chaotic system and a turbulent system? Is there any difference? Or
the chaotic system goes with the ODEs. So it is only chaotic dynamics in time. This, as you can, I mean, the time over here was there, I mean, because there was a basic, but one was looking at spatial patterns, which is not a part of the chaotic dynamics. The chaotic dynamics is not interested in, if I were to do chaotic, I would simply look at V as solve the equation for the velocity field as a function of time and find a very complicated and look at sensitivity to initial conditions and so on. But I mean, the turbulence people want to look at the spatial dependence, which is not a part of the chaos literature. Yeah.
Thank you.
That's the only, that's the difference.
So does that mean that this chaotic,
Yeah.
Does that mean that this chaotic behavior can happen at all length scales at each of those wave numbers?
Right. I mean, there is chaotic flow at every scale. Yes.
I see. Okay.
Yeah. And it is out of that every scale that you want to pick some feature out.
This is on something that you have not covered, but I think you have done some work on this new thing called bacterial turbulence.
Yeah.
So people find different kind of spectra and so on. So if your insight on this.
Well, I mean, it is more or less like the one which I talked about, where the point was that the velocity nonlinearity, the Navier-Stokes equation had a stress tensor which came from the concentration of the whatever was flowing around inside the fluid. So as I call it bacteria, call it what have you. So it was that nonlinearity was used in as the driving nonlinearity as opposed to the V dot grad V. So if I use that as the nonlinearity over there and then use the standard diffusion equation for the concentration variable, we get into a different cross. Over here it was the minus 5/3 crossing over to the 11/5. Over there we get into a different kind of crossover, one where the nonlinearity in the this what do you call it? I mean, if I were to do this as a virial expansion, there's a Burnett, second order Burnett term, which the fluid that in the Navier-Stokes equation, if you have some density, right, there is a conserved quantity appropriately formed out of the, so which is called, so where that Burnett term dominating, you have one kind of spectrum, and the other is the, So it's a crossover, but with the driver being the Burnett term over there. So you can have three parts over there. You can have the Burnett term driving, you can have the V dot grad V driving, so that's one, and then you can have the other driving. So so you can actually have three of them a crossover. But the essential feature was having a driver in the Navier-Stokes equation, which is in turn related to a modification of model H of critical, which Michael Cates and company had done some years ago.